Hello and Assalamu alaikum students. Last time we discussed discrete probability distributions, and now we will discuss continuous probability distributions. So let us recap the definition of continuous probability distributions. This is the probability distribution of a continuous variable, means the variable that can be expressed on a continuous scale. The probability distribution of such a variable is called as continuous probability distribution. And how it was determined using the probability distribution graph, if you can recall, in the discrete probability distribution it was the height of the line of the probability, while in continuous probability distribution it was the area under the curve between a certain interval. Okay, so let's go towards our first probability distribution. Normal probability distribution is one of the very important continuous probability distributions. So it can be expressed using this mathematical model or mathematical formula, or the function, whatever you want to call it. We can use this formula to express or represent normal probability distribution of a variable x is equal to 1 over sigma times square root of 2 pi and whole times x exponential raised to the power minus 1 over 2 times the square of x minus mu over sigma. Here mu is the standard deviation of the probability distribution, and mu is the mean of that mean of that probability distribution. The variable x can acquire any value between minus infinity and infinity. Because this is a continuous variable, so it can have any value between minus infinity and infinity on the number line. Okay, so there is no limit that it can be a digit only, or it can have discrete values only. It can have certain values and certain cannot. It can have any value between minus infinity and infinity, because this is a continuous variable. Okay, now this is how it looks like. This is how normal distribution looks like, and we have a specific name for it. We call it bell-shaped curve. Okay, and this curve is symmetric about the mean of the distribution. This one mu, it is symmetric about this mean value. It lies in the center and it is symmetric on both sides of it, and its expansion is related with the variance of that data. Now this curve has specific characteristics that can be expressed, like how much of the data is represented in how much means in under what area of the graph, because the area under the graph is actually the probability distribution, or the probability of certain values to occur. So it is very important to know how much data is covered under how much of the graph. So this is the graph, the same one, bell-shaped normal distribution. Its mean, or it is symmetric about mean. This mean lies just in the center, and we can divide it into standard deviations, into number of standard deviations. So if this is the mean, this is plus one mean plus one standard deviation, then mean plus another standard deviation, plus mean and another standard deviation. So this is mean plus one standard deviation, mean plus two standard deviations, and mean plus three standard deviations. And similarly on the left hand side, this is mean minus one standard deviation, mean minus two standard deviation, and mean minus three standard deviation, and it is written like this. So now we already know that the area covered between from minus 1 standard deviation to plus standard deviation is how much, and from minus 2 standard deviation to plus 2 standard deviation is how much, and from minus 3 standard deviation to plus 3 standard deviation how much it is. So this is how it is given. So from -1 sigma means the standard deviation is sigma, so we can call it from -1 sigma to +1 sigma. So this -1 sigma and +1 sigma is from the mean value. Okay, just remember that this is from the mean. We add 1 sigma to the mean and we subtract 1 sigma from the mean. So from -1 sigma to +1 sigma means within this region it contains 68.26% of the area. So the probability between -1 sigma to 1 sigma is 68.26, or the percentage of the data that lies between -1 sigma to +1 sigma is 68.26%. 68.26% of the data lies between -1 sigma to +1 sigma. And similarly, we can go to the next one, -2 sigma to +2 sigma. It has the area under the curve which is 95.46%. So we can say that the probability distribution, or the probability within of something to occur between -2 sigma to +2 sigma is 95.46%. And the maximum one, we can say that between +3 sigma to -3 sigma, almost all of the data is in between these three standard deviations from the mean value. Okay, so in the normal distribution, you should remember that in a normal distribution, most of the data, like here we can see, it is 99.73% of the data lies between three standard deviations from the mean. Okay, so this is important for you to know and remember. So this is the characteristic of standard normal distribution, that within +1 and -1 sigma it has 68.26% of the data, and from -2 to +2 sigma it has 95.46%, and from -3 to +3 it has 99.73% of the data that lies between -3 to +3 sigma, or lies between three standard deviations from the mean value. Okay, so you must remember that, it will be very helpful. Okay, now normal distribution can have all different values for mu and sigma. So in order to make it easier for us to find out the values for normal distribution, we can standardize a procedure. So first we need to define cumulative normal probability distribution. This is the probability distribution that is of the random variable that is less than or equal to a certain value. Let's say a, means that we want to if you want to find out the probability of x for values from -infinity to a certain value a, that will be called as cumulative, means all summed up together from -infinity until a. Why -infinity? Because x can have any value between -infinity to +infinity. So for cumulative, we take values from -infinity until a certain value a. We are calling it a. It can be 10, 11, 12, 13, 14, whatever that is. So from -infinity until that value is called as cumulative normal distribution. And how we can do it? It is represented like this. P means the probability of x having values less than or equal to a. If you remember that in discrete probability distributions we have equal, okay, it means x is equal to a certain value, right? But here in normal distribution, here cumulative normal distribution, we have x less than or equal to a, means all values less than until value A is the cumulative probability distribution. It is also represented as f of A. Okay, so the f is cumulative probability of x for all values of x until A. Okay, and since we know that it is area under the curve, right? So if means the probability of a continuous variable is equal to area under the curve between a certain interval. So interval here will be from minus infinity until A, because this is the area within which we want to of which we want to calculate the probability of. Okay, so we take values from 0, we take values under the curve from minus infinity until A. Okay, and then we'll integrate it, because integration is used for finding area under the curve, right? And rest is the same formula, 1 over sigma times square root of 2 pi multiplied by exponential raised to the power minus 1 over 2 x square of my x minus mu over sigma dx. So we will perform integration and we will get the cumulative probability distribution. Now how to get standard terms for this? So because in normal practice this probability distribution can have any value of sigma and any value of mu, right? So we can have a standard variable from this that we can extract from this. So that is represented with z. This is a standard normal variable, and we calculate it by using x minus mu divided by sigma. So x is the value of x, mu is the mean of that distribution, and sigma is standard deviation of that probability distribution. Okay, by doing this, what will happen is it will convert, or it will transform normal probability distribution it will still stay the normal probability distribution, but the value of mu can be changed from any value to 0 specifically, and sigma to 1. So when we standardize, when we use z variable instead of x, or we convert x into z, our normal probability distribution, the shape remains the same, but the mean value becomes 0, the mu turns 0, and sigma becomes 1. Okay, from here it can the probability or distribution of x can have any value of mu or sigma, but when we convert or when we transform x into z, then our normal probability distribution will have mu which is equal to 0 and sigma will be equal to 1. So this is called as standardization, and the z is called as standard normal variable. Okay, and if when we do that, we can write this expression like this. So this one, x less than a less than or equal to a can be written like this in terms of z, because we have, once we transform it into z, we can replace it with z variable. Okay, and this value a will be equal to a minus mu over sigma. Okay, and in short we can represent it like this, and this is called as standard normal distribution function. Then we will have mean equal to 0 and variance equals to 1. So what is the benefit of z? Once we have calculated this value, we can use a standard table. We have one table for area under the curve, finding areas under the curve, and that is for standard normal variable, because whenever we have a normal distribution, we convert it into standard normal variable, and then we can use that variable to trace its value on this table. For example, if after calculation the value of z, we get minus 3.05, so this column represent values of z, minus 3.0, and then we'll on the rows we'll locate the second decimal point, 0.05, so minus 3.05 intersection comes here, and this one represents area within that region. So minus 3.5 value has minus 3.05 value has area under the curve of 0.0011. So this one is actually the probability and within that region. Okay, let's do an example for normal probability distribution. In this example, the statement says that the tensile strength of paper used to make grocery bags is an important quality characteristic. It is known that the strength, let's say x, the strength is a variable which is represented with x, has normal distribution. Okay, so means that it is if you get this statement in the question, you are already told in the statement that x is a variable, means strength is a variable represented with x, and it has normal distribution with mean is equal to 40 pounds per square inches. The mean or mu of this distribution, which lies in the center of the curve or the probability distribution, it is at 40 pounds per square inches, and its standard deviation is 2 pounds per square inch, and it is represented with this notation n40 and 22. So this is how it is represented. You remember that n, and the first in the bracket, the first term is mu, and the second term is the standard deviation, right? So the purchaser of the bags requires them to have strength of at least 35 pounds per square inches. Okay, so this is the requirement of the purchaser or the customer. So we are asked to calculate the probability that bags produced from this paper, the one mentioned earlier, will meet or exceed the specification. What is that specification? That it should have a strength of at least 35 pounds per square inches. At least means that it should have 35 pounds per square inches or higher strength. Okay, so you have to remember, means note this thing, that x, which was the variable, this one which represents tensile strength, must have a value of 35 or above pounds per square inches. Okay, now we can write from this statement that probability of x is larger than or 35 that we have to calculate, right? So here we are going to make use of the concept of cumulative probability distribution. Okay, so how we do that? But in the cumulative probability distribution, our understanding was that the probability that we find is from the minimum value of x to a certain value, right? But this one is opposite. This is starting from 35 and going upwards, right? So we have a workaround to do that. So the probability you have to keep in mind to in order to understand this equation is that the total probability or the maximum probability is equal to 1, or in other words you can say that the total area under the probability distribution graph is equal to 1. So here the total probability will be equal to the all probabilities below 35 plus all probabilities or all numbers of the probability of all numbers above 35 is equal to 1, right? Because total probability is equal to 1. So here specifically we can say that the probabilities of the probability of all values below x plus all the probability of all values below 35 plus probability of all values above 35 is equal to 1, right? So from here we can rearrange the terms to get this value. Means it should have been probability of x greater than or equal to 35 plus probability of x less than or equal to 35 is equal to 1. So we are taking this term from the left hand side of equation to the right hand side, and it gives us this form, that probability of x having values above or equal to 35 is equal to 1 minus probability of x having values below or equal to 35, and this is the value for cumulative probability distribution. Why do we need to do this? Because we are going to make use of the probability distribution table, right? And the table gives us values from 0 until, or from the minimum value minimum value of x until this value, right? So for that, in order to use that table, we have to
do this thing. Okay, now we have to do one more step before we could go to table and find out the value for this probability. That thing is to transform x into standard variable. What was that? That was z. And how we do that? Like this: z is equal to x minus mu over sigma. So x is 35 and the mu is 40 as you're given here. Mu is 40 and sigma is 2 as you're given here. Okay, so that's how we can find out the value of z. Now we have to go to the table in order to find out the value of z, but first we need to complete this calculation. Like, it will be equal to, after we do it, means 35 minus 40 is 5, divided by 2 makes it 2.5, but since 35 is smaller than 40, it will be minus 5 divided by 2 is minus 2.5, or we can represent it like this. This was what this was this was standard normal. Okay, now we have to go to the table and find out the value for z is equal to minus 2.5. so when we locate the value for minus 2.5, that it means that all the probabilities below until minus 2.5. okay, so it doesn't mean that in the table the value, that if we are going to locate minus 2.5, the probability will not be for minus 2.5, it will be probability for all values below until minus 2.5. okay, now let's go to the table. This is the table. So this on the top of the table, the probability distribution graph is given to you, and this one, as you can see, it represents the value of z here. So if z is here, the highlighted region is the value which is given in the table. So if we have the value of z here, the value that we are getting from the table include the probability of this highlighted region. All of it means from left, or the minimum value of z, until this value. This is cumulative probability, right? So since in our problem it is our example problem, it is minus 2.5, so we can look for z. This column, the first column is the z, and this one is the second decimal number, right? So if, for example, we have 3.45, 3.4 is here, and we have to locate 0.05 here, then we go down and see. Okay, since ours is minus 2.50, so this is minus 2.5, and we do not need to go to any of these because it is 2.50, so we have to remain to the first column. So minus 2.5, and this first column, it is 0.0062, and minus 2.5 will lie somewhere around here. Okay, and this 0.0062 is all the values from here until here. Okay, so it will be around here until here, 0.0062. Now let's go back to our problem. Okay, now we have located it on the table. That was 0.0062. Now let's see how we can represent it on the graph. This is how we can represent it on the probability distribution graph. This one is for standard variable, and this one is for the normal one, this one. So you can see that the central line, which is the mu or mean value, it is 40 as given this, and 0.0062 is for 35 and below, right? Because this point minus 2.5 was the converted value for 35. X was 35 and corresponding z is minus 2.5. So 35 and below is 0.0062, but in the question we were asked to find probability for 35 and above, not below. So we have found below 35 and below, and we also know that this total is equal to 1. So in order to find this one, because this part, this non-highlighted part, is 35 and above, right? We need to find out this one, the probability under this region. So what we are going to do, 1 minus this thing. Okay, so this graph is for the normal distribution, this one is for standard normal distribution. Now you can see instead of the mean value 40, its mean value is 0, and 35 is converted to minus 2.5, because on the left hand side of the 0 the values are negative, on the right hand side these are positive. Okay, so after conversion the shape almost remains the same, but the values on the x-axis change. The standard deviation also change. The standard deviation, whatever that was before, it becomes 1. Okay, so this highlighted region here represents all the probabilities below until minus 2.5, or cumulative probability at minus 2.5. Since we are asked to calculate probabilities for 35 and above, or minus 2.5 or above, we will do the subtraction. How we do this? We just insert this value in equation 1 like this. So we have inserted minus 0.0062 here, and we get this value 0.9938. so this is the probability that we are going to get for the probability that the bags will at least meet or exceed the specification, and the specification was the tensile strength of 35 pounds per square inches. Okay, so I hope you understand this problem. If you have any question, we can discuss it.
Now, central limit theorem implies that the sum of n independently distributed random variables is approximately normal regardless of the distributions of the individual variables. So means that if we have n random variables which are independent of each other, means they do not depend on each other, so they will have their own independent distributions also. Okay, so they can have any different type of distributions, but when we sum them together, then the distribution becomes approximately normal. Okay, and it is and this approximation improves when the number of variables increases. If we have so many, a large number of n, or means a large number of independent random variables, then the approximation becomes better. Approximation becomes better means that their normal distribution improves, so it is more closer to normal distribution. If we have less numbers, sometimes it doesn't, this approximation does not work well, but sometimes it does. But that approximation always improves when we have more number of random variables, and then we sum them together, and then we get their distribution which is approximately close to the normal distribution. So this approximation will be satisfactory when there are many in many cases where it can be satisfactorily approximated by normal distribution when n is less than 10, means there are less than 10 variables, not the values but less than 10 variables. Okay, in some cases it has to be so many more, like it should be more than 100 to satisfy this the central tendency, or to satisfy the normal probability distribution. And in general, if xi are the identically distributed, means they have similar distributions. The xi represent different variables. Okay, I represent is the descriptor to indicate different variables, means x1, x2, x3 and x4. So if they have identical distributions, the distribution of each xi does not depart radically from the normal. Okay, then the central limit theorem works quite well for n is larger or equal to 3 or 4, means only if we have only 3 different types of 3 different independent variables, it can work with only 3 or 4 also. Okay, means that this approximation will hold well if there are variables which have identical distributions. Okay, now if there are x1 until xn, means there are n independent variables which are represented by x1, x2, x3 and so on up until xn. If these are the independent random variables, just like before we saw in the previous slide in the definition, so if we have those and their distribution has the mean value of mu I and their variance is sigma I square, then and if y is equal to the sum of all of them, so if y is equal to sum of all of these variables, then their distribution will be represented like this, and this distribution will have a normal approach, or it will show a bell-shaped curve, right, or it will be a normal distribution. So it will be perfectly normal, like it will approach to normal distribution with mu is equal to 0 and sigma is equal to 1 when n approaches to infinity, means that when these variable, the number of these variables approach to infinity, means the larger the number of variables are, the better is the approximation of this distribution to the normal distribution. Okay, now another another continuous probability distribution is exponential distribution, and you are already aware of what an exponential function is. It is related with that. So the exponential distribution is expressed with this mathematical model or formula or function, fx is equal to lambda exponential raised to the power minus lambda x, where x is always positive or 0 or positive, and lambda here is a constant value which is also positive. Here this lambda actually represents the magnitude or the scale of this function. Okay, because we have amplitude of the graph also, so it will look like this. This is how an exponential distribution looks like. So there are 3 different values of lambda which are generating 3 different curves, but they always look like this, look like an exponential curve or exponential decay, right? So this one, if you look at this one, the first one 0.2, the value of lambda is 0.2, it is representing the maximum value of the graph, which is 0.2. This one is 0.1, it starts from 0.1, and this one is 0.0067, this one is here 0.0067. so this is the scaling factor. So this lambda here is the scaling factor for the exponential distribution. Now the mean and the variance for this distribution can be find out using these formulas. Very simple. Mu is equal to 1 over lambda and sigma square is equal to 1 over lambda square. So we can very easily calculate the mean and standard deviation for the variance for this exponential probability distribution, and for standard deviation we can simply take a square root of it and we get standard deviation. Now cumulative exponential distribution, similarly like we saw for the normal distribution, cumulative normal distribution, we have cumulative exponential distribution also. It also means the same distribution of the means the probability of a variable from minus infinity until certain value, but here since x is from 0 until a certain value, it is not going to minus infinity, means that we can have from 0 until a certain point. Okay, so here if fa is the cumulative probability distribution of x below a certain value of a this is note that it is below or equal to the value of a, okay, starting from the least value until the value of a, and this is the probability of that. So, and we know that under continuous probability distribution, it is the area under the curve which is calculated by doing integration within the limits of the given variable. Okay, so limits from 0 to a times this function, right, this function here. Okay, so don't confuse yourself here. We have replaced x with t. Okay, this is the in order to differentiate it, okay, in order to distinct it from the previous one. Okay, so just note that in normal probability distribution it was from minus infinity to a. Now it is from 0 to a, because in normal probability distribution the value of x was starting from minus infinity, right, and it was going to positive infinity, right, plus infinity. But in exponential distribution its minimum value starts from 0. Okay, that's why we are using the limit of the integration from 0 until a, and we are using the same function here. Then we perform integration to get the probability distribution. Okay, now we can write it like this after this integration for all values above 0. Okay, and how it looks like, the curve, how the curve of cumulative exponential distribution looks like. It looks like this. Okay, it is different from the exponential curve. So it goes on, it increases, means abruptly, then it slows down, and it essentially becomes almost constant as the value of a increases. So it's means its rise decreases, it rises very slow or almost becomes constant. Okay, so this is how cumulative exponential distribution looks like. Let's go towards log normal distribution. So log normal distribution, there are two terms here, log and normal distribution. Okay, so if we have a random variable that is omega, you have to keep in mind that when we are talking about probability distributions here, we are always considering random variables. Okay, randomness is very important. So we have a random variable w that is related with another variable x through an exponential function like this, means x is equal to exponential omega, this is w. So this it can be written like this or like this. Both are equivalent, both are identical notations. Okay, so x is equal to exponential w or x is equal to e raised to the power w, both means the same thing. Okay, if these two variables w and x are related to each other through an exponential function, then if this one w has a normal distribution, then x will have a distribution that is called as log normal distribution. The name is means I will repeat that if w has a normal distribution, then x will have log normal distribution, and the name is given because of this transformation, that if we take natural log on both sides, it gives us this value, log of x is equal to w. Now you can see that if this one has normal distribution, this one has log normal distribution. Okay, very easy, right? And the probability distribution of log normal distribution can be expressed as this. Again, if we assume that x probability for x starting from the minimum value until a is expressed like this, then we can write it like this, right? So this is very simple, just like before, and we can convert it into standard variable also, like we did before. X minus theta, that was, if you recall the formula, that was x minus mu over sigma. here mu is represented by theta, and omega is represented the sigma is represented with omega. They mean the same thing. This is mean and this is standard deviation. Okay, this is this is x minus mu over sigma, log of a minus theta over omega. So they mean the same thing, only the notations are different. Okay, now the log normal distribution can be expressed with this formula. If you notice that it is just like the normal distribution formula. That was, if you remember, that was 1 over x sigma times square root of 2 pi multiplied by exponential minus 1 over 2 x minus mu over sigma, right? You remember that, right? So this is exactly the same, just this one is replaced, right? So this is now log of x instead of x, and we have replaced omega sigma with omega and mu with theta, right? So, but its values will be from 0 until infinity, positive. This is all only positive values, right? And this is how it looks like. You can relate it with normal distribution also, but it is a little bit skewed. It is skewed towards the left side, right? So normal distribution is just in the middle, okay, but this one is skewed towards left, right? So this is so if we change the values of the variance here, so omega square is equal to 2.25, then we have this graph, this shrunken there, this a bit darker one, and then if we have omega square is equal to 1, we have this black, and then we have lighter tone of this one, then omega square 2.25, we have this graph, right? So this is log normal distribution, right? So it has a bit of mix, it is a bit mixture of, you can say that, normal distribution and exponential graph, right? So this later part is the exponential decay, right? So it looks like the mixture of exponential and normal, but this is log normal distribution. And in this log normal distribution, the variance and mean can be calculated using these formulas very simply. Mu is equal to exponential raised to the power theta plus omega square over 2. This theta again, this is the mean, and omega square is the variance, right? If it is omega, this is standard deviation. If this is omega square, it is variance. Okay, now Weibull distribution. This one can be defined using this mathematical model. Here fx is equal to beta over theta times x over theta raised to the power beta minus 1 exponential minus x over theta raised to the power beta, and here the x assumes values from 0 until onwards, so x will always have positive value. Here x is scale parameter, called scale parameter, and beta is the shape parameter. You will see that by changing x we change the scale, and by changing the value of beta, here we change the shape of the graph of the Weibull distribution. In this this is how its shapes and of the graph looks like. So if you notice that we are changing the values of beta, keeping the theta same, equals to 1. Theta here means mean value, okay? So theta remains same, but by changing value of beta, which we call here as shape parameter, the shapes of these graphs is changing, right? So that is why we call this one as shape parameter, and by changing the value of x we can change the scale or size of the graph, okay? But we are keeping theta constant. You can see the shapes of these are changing by changing the values of beta. The mean and variance of this distribution can be calculated using these formulas. Now, cumulative probability distribution of Weibull can be calculated like this one, using this expression fa is equal to 1 minus exponential minus this part, okay, 1 minus this part here. And the importance of this is for these calculating these things in quality engineering. So Weibull distribution is used extensively in reliability engineering as a model to time to failure. So when we are assessing some devices, evaluating them, with the quality of them, we have to measure the time of failure. So time of failure means that how long does it take for a device to fail, means what is the this time to fail of that device. So reliability engineers or quality control engineers can model time to failure, the probability of time to failure of the devices for electronic or mechanical components using this distribution. So such as electronic devices, such as memory elements, mechanical components such as bearings, and structural elements in aircrafts and automobiles. So the time to failure for these parts, electronic parts and mechanical parts, can be modeled using this probability distribution.